Hello, everyone. My name is Fabrizio Sossan, and I'm an associate professor at the Mines Paris PSL in France. Before starting with my presentation, I would like to thank Professor Zekon Hu from Tsinghua University for organizing this panel and for having invited me to have a presentation here. The title of my talk is Grid Integration of Electric Vehicles, Flexibility Options of Autonomous Driving. It's a work that has been supported by the EVA project, whose website is here in the right-hand side of the title slide. And it's based on the work described here in the footnote of the slide, the impact of the charging demand of electric vehicles on distribution grids, a comparison between autonomous and non-autonomous driving that is going to be presented at the next IEEE EVA conference to be held in September 2020 that has been postponed due to the COVID-19 circumstances. So the context of the presentation is that the coordinated charging of many electric vehicles can lead to exceeding line capacity, statutory voltage limits, and substation transforming rating. It's a fairly well-known problem in the literature, and indeed there have been many smart charging algorithms that has been proposed to achieve coordination among EVs and avoid congestions so as to postpone expensive network reinforcements. The research question of this presentation lies in the domain of autonomous electric vehicles. We know that autonomous EVs will replace conventional EVs in the next decades. And thanks to autonomous driving, autonomous EVs can pick a suitable charging station autonomously and support local distribution grid operations. The research question that we tackle in this paper is how we can augment smart charging algorithms to use the option of autonomous driving to improve charging times and reduce grid congestions. And to reply to this question, we formulate an optimal power flow based smart charging algorithm for both EVs and autonomous EVs, and we compare their performance. So we start with defining the model of the battery state of charge of the electric vehicles. So we introduce first the charging power of a vehicle V at time t, which is denoted by uppercase PEV. And we say that uppercase PEV at times t and for vehicle V is non-negative because at the current stage we consider unidirectional charging scheme. The extension to vehicle to grid configurations where EVs can inject power back to the grid is however possible even in the proposed formulation. So once we have the charging power, we can define a model for the battery state of charge that is simply a discrete time integral of the power weighted for the battery capacity, where we add the efficiency eta, the efficiency term here that multiplies the charging power. Also, we say that as an additional operational constraints, we want the charging power to be less than the apparent power rating of the charger, that here is denoting, we denote this limit by capital P bar EV. And in this case, we note that we neglect reactive power, so we assume that the EVs cannot operate essentially at unitary power factor. And the reason for this is that we consider a fairly little low voltage network where the case of reactive power is not of special interest. However, it can be also accommodated in the formulation without too many complications. Also, we say that the indexes for vehicles and times respectively go from 1 to uppercase V and from 1 to uppercase D. So once we have the charging demand of the vehicles, we can define also the grid nodal injections. So we say that the real power injections at time t and grid node n is given by the sum of the net demand and the charging demand of all the vehicles connected to n. So here you see this is the nodal injection, and here we have the power demand, the net power demand, and then here we do a sum of all the vehicles and we consider the charging demand of all the vehicles. However, we weight the charging demand of the vehicles by the variable B, that is a binary variable that is 1 when vehicle V charges at node N, and it is 0 otherwise. So we can say that for non-autonomous EVs, the binary variable B is essentially defined by the final parking location of the vehicle, whereas in the case of autonomous EVs, the binary variable B is a free variable because the vehicle can pick independently a charging location. So by playing with this equation, essentially we are able to formulate a problem for both non-autonomous EVs and for autonomous EVs. We will also say that our grid has capital N index and lowercase n is the index for the node. So this is the formulation of the optimal power flow based smart charging problem. It's a conventional optimal power flow where we optimize some cost function, and then we have grid constraints, linearized grid constraints based on sensitivity coefficients. So let's say in details the formulation. In the cost function, our objective is to reach the target state of charge level that we denote with the SOC star. And we want to reach it as soon as possible, and we do so by minimizing the squared deviation summed over time. And we do this for all the vehicles. If we have, for instance, an electricity price, we can also minimize the cost of imported electricity. This is a choice that is normally up to the designer of the problem. In our case, we just want to reach the target state of charge as soon as possible, just to maximize the driver comfort, so that the drivers have always their vehicles ready to go and drive. So the first three constraints refer to the state of charge model, the SOC limits. In this case, we have 0 and 1, but of course, these are input parameters, so we can have whatever value we want. And we also have the charger limits. Then we have the model for the nodal injections, where B star and V here are all, for all nodes N and V are input parameters, and essentially defined by the parking locations of the final parking location of the non-autonomous electric vehicles, which also corresponds to their charging location. Then here we have the models, the equations of the grid model. So we have a model for the voltage, a model for the current, while the lower script L denotes the line. And then finally, we have also the power flow, the complex power at the substation transformer. And we have this for all the time and the nodes and current. And then finally, once we have these values here, we can use them to enforce grid constraints that refer to respecting statutory voltage limits, for instance, 10% in low voltage. Here we have the ampacity limits of the cable, and here we have the rating of the substation transformer. So how do we extend the previous formulation to the case of autonomous electric vehicles? Well, as said, the trick is essentially to let this binary variable be a decision variable of the problem. However, if we do so, we have some computational problems, as here we have the product between two decision variables, and this is a bilinear term, which is rather expensive to solve. Therefore, what we do is that we propose to use McCormick envelopes, so as to rewrite the bilinear term that here we rewrite in terms of a new variable z as a set of the following three linear inequalities, which for the case of when B is binary and P is bounded, actually these three inequalities hold tight, and so this set of three inequalities are actually an exact relaxation of the original problem. And this is pretty easy to see, because if we, for instance, say that B should equal 0, so that B is 0, here Z should be 0, and indeed here we have that Z is upper bounded by 0, and here we have that Z is lower bounded by 0, so Z has to be 0, and vice versa. When B is 1, then this Z should equal to P, and indeed here we have that Z is upper bounded by P, and is lower bounded by P. So again, Z has to be P. So let's see the formulation of the smart charging problem for autonomous EVs. It is exactly the same formulation as we have seen before for non-autonomous EVs. However, there are a few differences. Well, the first and most notable difference, as we have already mentioned, is that the binary variables here for all the nodes N and the vehicles V are now decision variable of the problem. So our problem becomes a mixed integer problem. Then we have what we call a non-multilocational constraints. This is a physical constraint, so as to ensure that the autonomous EVs charge at one node only for all V, and this is necessary. Then we have the new formulation of the nodal injections with the McCormick exact relaxations. Finally, we also apply two pre and post processing heuristics to model the additional charging demand associated to autonomous driving. Of course, autonomous electric vehicles can drive autonomously, so we should capture the energy that is consumed in the autonomous paths. So the first one is that if the residual state of charge of a vehicle is less than a threshold, then the vehicle should charge locally. And the second one is that if the final state of the final SOC of all autonomous vehicles that have changed location is decreased to account for the energy consumed when returning back to the original parking location. However, like in our case study, we cannot really appreciate much these two heuristic methods that, by the way, can also be implemented as linearly as additional linear constraints in the problem. I was saying that our case study is very little, and we cannot really appreciate the impact of the autonomous drive because the driving distances are very small. So this is the case study that we use for the comparison between EVs and autonomous EVs. We use the SIGRE benchmark system for low voltage grid. In this case, we use a single phase equivalent for an initial proof of concept. Of course, like especially in low voltage system, we have to extend to 3 phases also to evaluate imbalances, and autonomous EVs can also play a role in helping to unbalance the loads. As you see here, the main feeder is pretty short, is probably around 300 meters in total. So here the driving distances that are implied here in this case study are very little. So the demand profile is also from SIGRE specifications. We assume voltage independent active power, and the active power is calculated assuming constant power factor. We have 98 EVs distributed in the network, considering 1 EV per household, and the number of households is approximated from the nominal demand at each node, and the EVs have 16 kilowatt-hour batteries. We assume 3.7 kilowatt chargers, and we assume that electric vehicles arrive at the point of recharging with the residual state of charge that follows the distribution. And then we assume that all EVs and their trips, and they're available for charging at the same time, 4 p.m., 4 in the afternoon. The time resolution of the results of the scheduling problem is 1 hour. We have a scheduling horizon that is 15 hour long, from 4 p.m. to 7 a.m. the next day. So these are the results. In the first plot, you can see the charging power across the population. In the second plot is the total charging power of the fleet of EVs. In the third plot is the SOC across the population. And then finally here in the fourth plot, in the bottom right corner, we have the nodal voltages in the grid. We have 2 colors, the red for non-autonomous EV and the green for autonomous EVs. And we have 2 shades of colors, the lighter shade that denotes the min max values, and the darker shade that denotes the 0.25 and 0.75 quantiles. So the observations that we can make are that the charging period of the conventional EVs, so for non-autonomous EVs, is split into 2. And the reason for this, so you can see here that the red line is like different than 0 here, and is different than 0 here, whereas it is not for the green line. And this is due to the fact that there are voltage congestions determined by the concomitance with the peak load of conventional demand. And then we can say that autonomous EVs achieve to recharge faster than EVs. And how is it possible, and where do the autonomous EVs go to charge? We can say this from these results. We see that in the case of autonomous EVs, node 15 and 18 lose a few vehicles, 7 vehicles here and 5 vehicles here, and they essentially go to charge in nodes that are closer to the grid connection point, where of course we can load the grid more because we are closer to the grid connection point. So as conclusions, we can say that autonomous EVs add an additional degree of freedom to the charge scheduling problem. Smart charging of autonomous EVs contributes to reducing congestions effectively thanks to selecting suitable charging points in the grid. We propose a smart charging algorithms for autonomous EVs with an optimal power flow augmented with binary variables and bilinear terms that are exactly linearized with Mukherjee envelopes. Still, the problem is, of course, non-convex because we have binary variables. And then I conclude with a final recommendation for distribution system operator, DSOs, where, of course, it's kind of intuitive that autonomous EVs will avoid grid congestion because they will be free to go charging everywhere and can, of course, postpone cable replacement. So if grid congestions are a problem for non-autonomous EVs, in the meanwhile of the transition to autonomous EVs to happen, DSOs can opt for temporary solutions to solve them, for instance, battery energy storage system. Thank you for your attention, and these are my references.